Hi folks, welcome back to Physics with Captain Rod. Making this video here to go through page 10 in your notes on circular motion. So what we're looking at is some sort of object like, I don't know, a rock or a hockey puck or something that is tied to a string, and it is undergoing circular motion on some sort of like frictionless tabletop. And we're going to go through a couple of calculations here. So let's see, the first one here, what is the object's speed? So when you're calculating the speed of an object that is moving in circular motion, I like to do it like this, right? Your speed, that's the magnitude of your velocity, I usually just put v for that, is equal to distance over time. And in this example, it says the object completes 5 revolutions in 6 seconds. And the length of the string is 0.5 meters. So what we can do from that is this. Oops, I forgot the numbers. Okay, 5 revolutions in 6 seconds. So what that means is that in 6-second time frame, the distance that that rock will travel is 5 times 2 pi r. The 5 is because the rock will go around 5 times, 5 revolutions, and the 2 pi r is the distance it will travel each revolution. And then we'll just divide that by the time it takes for that to occur. And I'll let you folks run that and make sure I did this right. But when I do that, I get 2.62 meters per second. Okay, part B, what is the acceleration of the object? So, again, I want to go back and chat about this more. Centripetal acceleration is, I think, a reasonably difficult thing to understand. So, we're going to look at like these time frames right here. And let me call this velocity your v initial here, and this one your v final. And just remember how basic math works. If I start with $3 and I add $2, I now have $5, right? It is a basic, I'll call it principle of the universe. If you take your starting amount and then you add your change, you get your final amount. This is true of all quantities, vectors or not. So in this example, okay, this is our starting velocity. So I'm going to draw a vector for that. V initial. The final velocity points this way. Call that V final. So the change in velocity points this way. All right, that's a really important thing to understand is how these vectors work. And again, let me go back to my previous discussion. Whatever you start with plus whatever your change is equals your new amount, or I'll call it your final amount here. This is my starting vector. This is my change in velocity. There is my new amount. And again, notice in the picture, these two are tip to tail. So that means vectorially, the initial plus the change in velocity equals my final velocity. And I really should have vector symbols over all of these. Again, just like over here, my starting amount plus my change equals my final amount. My starting vector, velocity vector, plus the change in velocity equals my new velocity. All right. So this type of acceleration, right, is what we call a centripetal acceleration. And when you calculate centripetal accelerations, they are equal to v squared over r, where the v is the speed and the r is the radius of curvature. And I'll let you check my math on this. I got 1.37 meter per second squared, or meter per second when I did that. Okay, part C, what is the tension in that string? So anytime you use Newton's second law, you should draw a free body. And right here I put a picture of that rock, and I'm going to draw the free body right at this location. Now what location you draw the free body at does not matter. And remember, strings, they pull. You can't effectively push anything with a string. If you take some yarn or a piece of twine or something and try to and try to straighten it out and use it like a pole and push something. It does not work very well. All right, but they can pull very effectively. So at this location, that string is pulling this way. So in my free body, my tension vector looks something like this. And it might be tempting to want to put some sort of outward force here. And I ask people about that, you know, and there is this gut tendency to want to say there is some sort of outward force. Well, there just isn't, right? That thing called a centrifugal force is just a figment of people's imaginations. There is no outward force. And the free body should not be balanced because the net force is not zero. There is a change in velocity, and therefore there is an acceleration. Therefore there is a net force. So that's the only force acting on this object at that location. The vertical forces would be coming at us and away from us. They're just not relevant here. They're not in directions that are relevant. So if we add up all forces in the direction of the acceleration, which was like basically up and left, that is going to equal ma, recognizing that that acceleration is a centripetal acceleration. And I got 13.7 newtons when I ran that. I'm not sure what this little mark is here. I'm just going to get rid of that. So I'll let you folks check my math and make sure that it works out. I hope that you enjoyed the video. Have a great day.